Join us on a voyage through the wormhole, your gateway to groundbreaking thinking on AI, space exploration, a healthy planet, and a more intelligent future. I'm your host, Jonathan Knowles.
The Wormhole is produced by Trillion Technologies, leading the application of artificial intelligence for planetary stewardship, space exploration, and human health. Help us explore what's over the event horizon by following us on LinkedIn and Twitter at trillium.tech. Together, let's build an intelligent future.
NASA has designated 2024 as Heliophysics' big year. And along with the eclipse that swept across much of North America, it's likely we are entering solar maximum, the regular period of greatest solar activity during the sun's 11-year solar cycle. During solar maximum, large numbers of sunspots appear, and the solar irradiance output grows, sometimes significantly. Those of you who joined in our discussion with Dr. Tom Berger will know that, in fact, the sun has been quite active recently, with several large coronal mass ejections resulting in significant geomagnetic storms. And speaking of eclipses, we hope you all had a fine eclipse day, and feel free to share in our various social media communities your eclipse experience photos. At FDL, we've been engaged in applied AI and heliophysics research for 7 years. And for this series, we are tapping into our faculty scientists who bring a wealth of knowledge and experience, as well as groundbreaking research that is significantly advancing our understanding of solar phenomena and their impacts on the solar system and here on Earth. Today, we hear from a good friend and colleague, Dr. Anna Jungbluth, a research fellow at the European Space Agency Climate Office, as we discuss the intersection of AI, solar science, and global climate dynamics. Anna works in machine learning applications for Earth observation and climate research. Before her postdoc, she obtained her PhD in physics at the University of Oxford, researching renewable energies. Throughout her PhD, Anna developed an interest in machine learning for scientific applications, which led her to joining FDL as a researcher in 2019. She returned to the program as a faculty member and helps lead various heliophysics and Earth observation projects. She is passionate about increasing diversity in STEM and helping to empower the next generation of interdisciplinary scientists. Welcome, Anna.
Hello, thanks so much for the invitation to be here.
Of course, it's always a pleasure to see you and very exciting to be able to have this conversation with you today. I think we're going to cover some real interesting stuff. One of the first things we like to do with any of the people that we are interviewing is ask them about their journey. So if you would, let's take a moment and talk about your journey to becoming a scientist who is focused on the domain of Earth observation and climate science, and how you ended up at the European Space Agency.
Yeah, so I was born and raised in Germany, and actually, have always been interested in science and technology and math, but probably hadn't always known that I wanted to be a scientist. I think for one, because when you're in school, you don't really know what it means to be a physicist. You just see your physics teacher, and that's all you imagine physics to be. But for instance, the vast diversity of jobs that you can have, I think, are sometimes hard to grasp when you're in school. But when I was younger, I actually wanted to be a fashion designer first, because I wanted to create fair trade and sustainable clothes. So it was always related to climate change, but that's what I wanted to do first. But then I realized two things. The first thing being that I'm not creative in that way. I'm creative in other ways, but maybe not in the design kind of way. And secondly, I thought that you had to be really extroverted and network your way to the top if you're working in a very creative field like that. And as someone who's an extroverted introvert, that didn't really seem like something that was what I wanted to get out of my career. Now, of course, as a scientist, I'm now discovering you have to be quite extroverted too and network with people and, present at venues like this. So, throughout practice, it's getting more and more comfortable and pleasant to do over the last couple of years. But yeah, so when I finished school, I was very interested in studying something related to science. I didn't really know what I wanted that to be. I figured physics was a good choice because it opens so many different doors and you're not really narrowing you down what area you want to specialize in. And I really wanted to get out of my little bubble that I had in Germany. So I applied to go to the US for my undergrad, which was a very transformative experience for me, being away from home and also just being in a different environment with different people and different mentalities. And I think a lot of what drives me today was really built throughout my undergrad when I was around a lot of people focused on science and technology and using science and technology for the betterment of the world, whatever that might mean. And so throughout my degree, I primarily took material science and physics classes and was doing a lot of work focused on renewable energy and specifically solar cells and solar energy. So when it came to making a decision for my PhD, that's what I applied to do, and then moved to the UK to start a PhD working on organic solar cells. I really loved doing that during my PhD. It was a very interesting topic of research, but I very quickly discovered that the parts of my work that I enjoyed the most were when I sat down at my computer and was programming, if that was data analysis or if that was building pieces of equipment and writing the code to run them. And I wasn't enjoying the lab work maybe quite enough to build my entire career on that. So throughout my PhD, I took some coding classes and taught myself a little bit more how to code, which is maybe a little bit the shout out that it's never too late to learn something new. And became a big believer in open source and open science, and was able to learn a lot and teach myself a lot throughout my PhD. And then, of course, at some point, I came across the Frontier Development Lab and the research that was being done there. And it was a little bit like, it felt like a bit of a shot in the dark, because I wasn't sure if my profile would really fit, not having done much machine learning before or having worked on solar physics or Earth observation projects. But I think my general mentality of wanting to work in interdisciplinary teams was very fitting. And so people gave me a chance, and I joined, as you've correctly said before, in 2019 as a researcher, and I worked on a project where we used machine learning for super resolution of solar magnetic field images, and learned a lot about solar physics during that time. And really, it opened my mind to the whole field of applying AI for science and trying to think of what metrics we might want to present so that scientists feel comfortable using the results of our models, but also how we can adapt existing models that have been developed for normal images and consumer applications to something that might be really useful for scientific applications. And so then I couldn't get enough, and basically every single year since then have come back to the program in the summer and led various different projects focused on solar physics. And when I got to the end of my PhD, I was very certain that I wanted to shift my career more in this area, but wanted to stay very much connected to climate change. So when I was looking for positions, I saw that there was postdoc opportunities at the European Space Agency and an opening in the Climate Office, which conveniently is based in the UK, where I also did my PhD. And I applied, and again had great people giving me a chance, and have now been working on machine learning applications for Earth observation for the last year and a half. And that's been really interesting. I think I learned a lot about new sources of data, how Earth observation is used for a lot of different areas of climate research, but I've also understood how valuable the experiences I've had working on heliophysics applications have been to learning about Earth observation, because at the end of the day, a lot of the fundamental principles of how the measurements are taken and how the data is structured is very similar. So I found it really relatively straightforward to switch, and now have knowledge in multiple different areas, which is great because it helps to connect things in a new and in a novel way. And so yeah, that's a short whistle stop of how I've ended up where I am now. And the Climate Office, where I'm based, and what you can also see in my background, is sort of the focal point of a lot of the climate change related activities that ESA has. And what my team does is they provide long-term data records of what's called essential climate variables. So there are about 55 essential climate variables defined that are chemical, physical, biological parameters that help describe our climate. And a lot of them can be observed from or measured from space. And so what my team does is they have a number of different projects where they try to derive these essential climate variables for land cover or atmospheric parameters or ocean parameters from satellite imagery, and providing long-term consistent data sets that people can then use for their climate research. So even though I don't really do that, I use a lot of this data in addition to other Earth observation data for various different applications using machine learning.
It really is the time of Earth observation, isn't it? Like never before in history, and we've been doing it for over 60 years now with the first Trios and Landsat satellites that were launched decades ago, and the various many that are up there now. So very exciting time for you to be there, and how wonderful that you fell in love with coding and specifically with AI. Let's talk about that just for a minute. You mentioned the project you did when you were in FDL. We have a lot of folks here joining us today for the live version of this that are just coming into the FDL program this year, a place you were in a few years ago as a newbie. What can you tell us a little bit about your particular project? You mentioned it, but go into just a little more detail, and then maybe share a little bit of wisdom with those who are just coming into the program.
My very first project was related to super resolution of solar magnetic field images. So basically, as it is for many different disciplines, Earth observation being one of them, we have a lot of different instruments that observe the sun and that observe the Earth. But just like with any camera, technologies improve throughout time. So and the sensors are limited. So we often have data over the span of 5, 10, maybe 20 years, but not decades and decades and centuries. And I mean, the age of satellites has really only started 30, 40 years ago. So we have a lot of data, but what's often needed is consistent, homogeneous data for you to be able to draw valuable conclusions from that. So this project was specifically focused on solar magnetic field images and trying to standardize them across different instruments that have measured the solar magnetic field with different resolutions, temporal cadence, instrument characteristics, noise levels, etc. And that kind of started sort of the interest in one of the two streams that I would categorize my research to be now. And specifically this idea of using machine learning to get the most out of archival data sets and standardizing data sets, doing instrument intercalibration, instrument-to-instrument translation, and getting the most out of the data that we already have. And then in following years, I've had the chance to work on sort of what I consider to be the second focus of my research, which is then using this data to get valuable scientific insights. And so one of the projects I worked on a couple of years ago was focused on using different vantage points of different satellites that look at the sun and stitching this data together so that we get 360-degree 4-pi representations of the sun. And the idea of deriving 3D information from 2D images is, of course, like just so incredibly interesting. And last year, I worked on a really interesting Earth observation project that was focused on creating foundation models. So using all of the unlabeled data that we have available to train a model and learn what Earth observation is, what types of features we want to see, and then refining these models for specific use cases. For instance, land cover classification, detecting vegetation, potentially looking at floods and fires. And I think that's a really, really exciting area of AI research as well, both for heliophysics and for Earth observation applications.
And what can you share with some of those new folks?
Yeah. I think what I've learned over the last couple of years is feeling comfortable with not being an expert in a room. I think very often we go through our careers, or academic careers in particular, with this goal of becoming the foremost expert. And it does happen during the PhD, but the area that you're an expert in is so incredibly niche that probably the amount of people you can talk to on like that high a technical depth and technical level you can count on one or two hands. And I think actually what you're learning is how to do research, how to organize your thoughts, and how to develop new knowledge and pick up new knowledge along the way. And, as you will have seen from, what my career has been so far, I worked on renewable energy, I worked on solar physics applications, I worked on Earth observation. So I wouldn't necessarily consider myself to be an expert in any one of them, but what I'm an expert in is sitting at the intersection of a lot of these different fields and being able to speak the language of multiple different communities. And I think that's a very, very valuable skill to have. And of course, in the context of applied machine learning to scientific disciplines, this is really where it's going, because machine learning experts don't necessarily know all of the details about a specific problem, and domain scientists might not necessarily know about the tools. So inevitably, you have to learn something that pushes you outside of your comfort zone. And I think the outcome of this now is that I feel very comfortable being in a room and not being the expert and not understanding every single acronym that people say and not being, immediately picking up on all the different details, but I trust that I can figure it out. And I'm very grateful to, the FDL ultimately for having fostered that in me. But I guess this is also my trajectory is an example that it's never too late to make shifts in your career, and actually really interesting things happen when you take non-linear paths, because you pick up things along the way that you wouldn't have picked up otherwise. And specifically in the context of a program like the FDL, where interdisciplinarity is everything, and we want people from different backgrounds working together to create something completely novel, I think it's just such a great thing. So definitely, been very grateful for the opportunity.
That is such excellent advice as a person who's a bit older than you, who's been, I have to use the word preaching that. You have articulated it absolutely wonderfully. And I hope everyone listening, whether they're just coming into the FDL program or not, listens to what you just said again, because I think it is absolutely critical for us to solve the challenges that we face here on Earth today. Thank you for sharing that. Let's talk a little bit now about the science, solar science, and the sun's variability, including solar cycles and solar flares and coronal mass ejections, and their effect on Earth's climate, which is really a very new thing. We're not sure what the answer to that question is, but what are your thoughts on that, on the big picture?
Yeah, I think this is a very, very interesting question. I mean, to start, the sun provides all energy that powers life as we know it and that powers our climate. So in a way, it influences everything. But there are different timescales on which we can look at this. So across very long timescales, what's probably the most important is Earth's orbit with respect to the sun, and specifically how ecliptic the orbit is, the tilt and the precession of the Earth with respect to the sun. And so here, this is related to ice ages and other types of climates that the Earth has experienced on hundreds of thousands and millions of years timescales. So for our lifetime, relatively stable, but across Earth's climate as a whole, very important. And so this is what's called the Milankovitch cycles. On much shorter timescales, it's very interesting and very difficult to understand the exact connection, because solar variability, so across the solar cycle, the total solar radiance that the Earth experiences from the sun, we have some disagreement on what the absolute value is, though we know roughly what it should be. But the variability across the solar cycle is actually very small. So that's 0.1%. And that is such a small variation that linking that with exact changes that we're seeing in weather and climate patterns is actually very tricky to do. A few pathways in which it's hypothesized that the sun might influence weather and climate patterns are, for one, if you have more solar radiation and you heat the ocean surface, then you might have more evaporation and thermodynamic coupling to the atmosphere, and that might influence weather patterns. You might have more absorption of specifically ultraviolet light in the atmosphere, which then heats the atmosphere and changes potentially weather patterns and couples to lower levels of the atmosphere. And sort of a proxy effect, I guess, in a way, is galactic cosmic rays. So galactic cosmic rays, which are high energy particles, a lot of protons that come from outside of the solar system. We experience them all the time, but we're often shielded by the sun's magnetic field. And through increasing solar activity, the magnetic field screens a lot of these galactic cosmic rays. So we tend to experience fewer of them during times of high solar activity. And there's some thinking that galactic cosmic rays can ionize the atmosphere and then potentially create nucleation sites for clouds. And so that might change as solar activity changes. Now, a big challenge, though, is to find correlations within what we're observing from solar activity and from Earth observation derived, or climate variables in general, to have correlations or causal links between that. So while a lot of these theories sound very plausible, to really pick out the very small nuanced changes is actually quite challenging. And of course, the important thing to say here is that it's very, very evident that climate change is not caused by changes in the solar variability. It might be a very, very small contribution, and whether it has any climate or whether relevant magnitude is still to be seen. And this is a very active and interesting area of research.
It's an interesting time because we are at that intersection where we're sort of moving beyond FEA models on supercomputers and into AI in order to do some of these models. So when we think of that as one interesting area of research, as well as just climate challenges in general, what kind of challenges are we faced with when we're trying to accurately model and quantify the sun's influence or just climate models? And how do we compare the various 55 or so predictors that you mentioned earlier? What are our challenges with regards to that?
Yeah, so I think one of the biggest challenges is related to the data that we have. So across long timescales, we don't really have direct measurements of solar irradiance, but we have proxy measurements. So for instance, the number of sunspots has been recorded since the 1600s, 1700s.
Galileo had his telescope up, right?
Yeah, exactly. The aurora has been documented probably since the 1800s. So we have proxy measurements that we can then convert into what we think was going on with the sun at the time. But of course, all of this conversion and deriving the long-term data records comes with its own uncertainties. Similar to this, now that we have satellites, so we've been able to measure solar irradiance with satellites since 1978. And we have a number of different satellites that have looked at the total solar irradiance and the spectral solar irradiance of the sun since around then. And while all of the satellites agree on the general, percent change across a solar cycle, and there's general agreement that is about 0.1% of the total solar radiance that changes between a solar minimum and a solar maximum, there's a lot of, some disagreement on what the exact number, the absolute value of the total solar radiance is. And that is challenging for a few different reasons. So for one, we need to know what energy we have available to be able to resolve Earth's energy budget and really know what's coming in and what's going out. Often these numbers are also used to calibrate climate models, so it influences that in a way too. And that's not to say that there's massive disagreements between them, but the uncertainty is large enough that it might drown out some of the very small effects that we might see from this 0.1 change in solar radiance. And then, of course, to exactly understand which parts of the solar spectrum change. So there's a lot of evidence that a lot of the extreme ultraviolet part of the spectrum changes a lot. And of course, a lot of that is filtered out in our atmosphere, observed in the upper layers of our atmosphere. And maybe the visible and the infrared part of the spectrum doesn't change so much, but there's still a lot of uncertainty on that. So in the future, there'll be additional missions that will look at this and really try to set a golden standard for what the total solar radiance and spectral solar radiance is. And one of them coming up at the end of the decade is called TRUTHS, which stands for Traceable Radiometry Underlying Terrestrial and Helio Studies. And that's led by the UK Space Agency and developed with ESA too. So that's with the goal to kind of help constrain the uncertainty on some of these values too. And that's going to be really helpful in being able to study the connections in an easier way.
That's a very exciting mission. I can't wait for that to move forward. I tell you what, we're going to do this. We're going to take a short break right now. Stay with us. We're talking with Dr. Anna Jungbluth from the ESA Climate Office, and we have much more to discuss. We'll be right back.
Thank you for joining us in the Wormhole. We'll be right back. The Wormhole connects you with scientists and experts from diverse fields, offering insights into their groundbreaking work and the passions that drive them. We sincerely hope that you will join us on these inspiring journeys into the heart of discovery and the power of ideas that are transforming our understanding of the universe, our planet, and ourselves.
Very good stuff so far. Let's shift a little now and talk about a little more about AI in all of this, and specifically machine learning. And for some people who might not be, as you mentioned earlier, and especially at FDL, we combine domain science folks with domain AI folks. And so when you, as a physicist, think about this, what's your answer to how can machine learning improve the accuracy of climate models from you've had both experiences now in ML and in physics. What do you think?
Yeah, I would definitely not consider myself to be an expert in climate models, but I've worked with enough people that I've absorbed some of their knowledge. And my understanding of climate models is that we have a lot of really great climate models. Of course, we want to include more and more parameters in them and couple oceans to the atmosphere, to the cryosphere, to land. And oftentimes these climate models can be quite expensive and time consuming to run. So AI might be able to help and bridge some of the gaps and emulate certain aspects of climate models. Ultimately, we're interested in having really high resolution models, both spatially sort of on Earth's surface or the ocean surface, but also vertically. We would like to resolve a lot more information than we might be able to run at the moment. So AI could come in really helpful there. But of course, also the idea of assimilating different data sets and bringing observational data into climate models, AI is really useful for. We've spoken a little bit about translating characteristics between different instruments. The same, approaches can be applied to comparing model outputs or model data to observational data. And I think that's where AI really shines when it comes to emulating characteristics of something based on a different type of input. So I think the general idea of increased resolution is definitely really interesting, and AI could be really helpful there. One thing that I've found out as well is, for instance, galactic cosmic rays, and we've spoken a little bit about the connection that they may or may not have to clouds in the atmosphere. A lot of these effects will be really, really small scale, and a lot of this is not currently included in climate models. So if we want to move towards being able to study the connection between the sun and climate and weather, these would be great opportunities to expand existing models.
So data. We've mentioned the word. Let's take a little tangent here. We've mentioned the word Earth observation a few times here. And let's talk about what Earth observation is, what its current state is. We've mentioned one particular ESA mission that's coming up that is adding to that, but what is it? What's the current state, and where do you see Earth observation going?
Yeah, so Earth observation, very broadly speaking, is the measurement of chemical, physical, biological parameters and measurements from space via satellites or via ground-based measurements or in situ measurements with balloons and airplanes. Of course, I'm biased because I work for ESA, so Earth observation using satellites I find incredibly interesting. And what I really like about it is the fact that, the ESA and NASA and big space agencies, they're funded by taxpayer money. So the data is publicly available for people to use. And I appreciate that there's still some level of domain knowledge that goes into interacting with this data. But I really like the idea that anyone can go online and look at data from the Sentinel satellites and look at what's going on. You can look at deforestation in the rainforest. You can look at eventually, I think where we're going is being able to detect methane and other types of emissions from space, and deriving country emissions from that, and not relying on reporting as the only source of understanding what the emissions of a specific country or a specific region or a specific company might be. We have a lot of different satellites that have collected data over the last couple of decades. So generally, they're split into polar orbiting satellites, which continuously orbit the Earth and collect global data over some time period. And we have access to geostationary satellites, which always look at the same place on Earth and have really high temporal resolution. And then you have the distinction between active satellites that send out radar, LiDAR pulses, and look what comes back, and passive satellites that look at different, that basically take images of the Earth in different spectral channels. And I guess specifically in the context of the conversation that we're having now, where we're talking about heliophysics and Earth observation, there are some satellites that do both at the same time. So for instance, NOAA's GOES satellites have instruments that look both at the sun and at the Earth. And of course, they're then really useful in being able to couple things in a little bit more of a way without having to go through the pathways of, correcting for orbits and projecting one thing into the reference frame of another and doing a bunch of other corrections to that. I guess related to where I see Earth observation going in the future, of course, there's always development of better satellites and launching new satellites that take measurements in a way that we haven't been able to do before. You also have to remember that often the lifetime of satellites is between 5 years and 20 years, right? So there needs to be some level of overhaul within that. But I think what's really exciting to see in the future, now that we have a few decades worth of data, what are we using this data for, right? You can do a lot of work for the point of doing science and accumulating new knowledge, but really what's going to become very interesting is how that data is being used for action, for Earth action, for mitigation and adaptation in the climate space. So I'm really excited to see what will come up in the future.
And of course, in addition to Earth observation, we have sun observation. We haven't been doing that quite as long with SOHO and SDO. For about 25 and 14 years, we've been collecting some pretty good data. And of course, ultimately, I imagine that is useful as we think about these models going forward, even though we know, with at least right now, it doesn't seem to have much of a impact on it, but it's certainly still useful and worthy to study what the sun is doing.
Most certainly with the sun, I think there's still a lot of frontiers for us to get to. And I know this has come up in the conversations with the previous experts about the Parker Solar Probe taking measurements, the closest now that we've ever been to the sun, and with the stereo satellites looking ahead and behind of Earth's perspective. I think there's still a lot of really interesting science to be done from new missions that might come up in the future.
We're just getting started with the sun, that's for sure. Are there any innovative AI projects focused on climate that you have paid attention to, that you can share with us, that are particularly worthy of someone looking into a little bit more?
I think there's a lot of really interesting AI research. Of course, the FDL projects from previous years are a good place to start. I specifically looking at the connection of sun and climate. I've been doing a little bit of research and I haven't found tons of papers that look at this connection using AI. So I think that's definitely still a really interesting area of research to be explored in the future. And I think AI, of course, with its ability to find patterns in large, vast amounts of data, might be able to make a lot of sense of that. And even though I'm not an expert on this, like causal methods and looking at attribution of different factors might be really interesting here, because we've spoken about this a little bit. Of course, everything's very connected, the sun and weather and climate and all of the cycles that we're seeing, irrespective of solar activity. I think maybe AI can help make sense of that. I think the projects I always like the most are the ones that come from a place of scientific understanding and using AI as an enabling tool to refine our understanding. I think there's a little bit of a fear of using AI as this black box tool and applying it to a scientific problem and hoping to get something out and then trusting it blindly, rather than approaching it from the place of knowing what the physical links would be and then hoping that the model learns that. So yeah, lots of interesting work. I think specifically because we're just getting started with AI applied to science, we're still at the place where a lot of important work needs to be done to create benchmarking data sets and benchmarking metrics and really set the baseline of what we want this work to be in the future. So that's something that I'm personally very interested in and always appreciate when I see that being thought about in publications.
Have you thought about what, in a perfect world, as they say, what you would do if you had access to all the data and unlimited compute power and someone said, go, do? What would you do?
I think, following up from the project I worked on most recently with the FDL for foundation models, I would want to train the biggest model that has seen all of the Earth observation data and make that available to the community. I think it would be really cool to see if space agencies like ESA in the future, in addition to providing data sets, also provided trained models for specific applications and the training that goes with that for the community to use it. So that would be, of course, incredible to see.
If you had to, place a bet or back a horse, as they say, where would you go? Surrogate modeling or foundation models? Which do you think will have the biggest impact on the next decade of science?
Oof, I think any and all of them could be
Good answer.
transformative, as long as we're, yeah. I mean, of course, I'm biased towards foundation models because that's something that I've worked on before, but I think surrogate modeling is also really, really interesting if it can help us run models with really high spatial and temporal resolution, on really fast timescales, as long as it's backed by scientific understanding. And of course, specifically for climate models, a big challenge that I'm curious to see how the AI field will solve it is that just learning from past data is not enough to predict what's coming. And I think that's going to be really interesting to see how the climate modeling community and the ML community will work together on coming to some consensus in that.
Nice. Let's talk just for a couple minutes about ethical considerations. That's, of course, a thing right now in anything to do with AI and to do with science in many cases, and certainly worthy of discussion. What are your thoughts on the ethical considerations of this kind of research that we're doing? What should we be paying attention to, safety and ethics here?
Yeah, I mean, of course, maybe generally speaking, when we're developing these models, there might be biases that are seeping into it that we can't anticipate beforehand. So having diverse teams working on these projects is really important. But specifically, I guess, in the context of the conversation that we've been having now, the link between the sun and climate change, it's very clear that solar variability is not causing climate change. Climate change is made by, is caused by man-made emissions of greenhouse gases. Yeah. And I think this is why these projects are so interesting, but need to be phrased in exactly the right context so that it's not blown out of proportion and fueling sort of the narrative of potential climate change deniers. What I found really interesting, though, is looking at the IPCC reports, so the United Nations Intergovernmental Panel on Climate Change, which publishes assessment reports of the physical science basis of climate change and sort of more focused on adaptation and mitigation. They provide information on radiative forcing, so how much different factors push the atmosphere's radiation budget out of balance. And solar variability is included in that, but with a really, really small contribution. And there's a lot of confidence in that, although the general scientific understanding is still relatively low. So it's a really worthwhile topic to study, put in the context of climate change is not caused by the sun, which of course, for ethical reasons is really important. But I think in general, when applying AI to a specific topic, we need to understand that AI isn't going to solve climate change, but it's a tool that can help us on our fight against climate change and moving towards a more just and sustainable future. And I think understanding that is really important, like understanding where AI is the most suitable and where it cannot help, and also understanding the hypocrisies that come with training large AI models that are run in big data centers that might consume a lot of energy is something we should always keep in mind when we're embarking on this research. AI is a tool, but it's not the solution.
It's been said before in various ways that technology won't solve our problems and our challenges. However, we're not likely to solve them without our technology.
Exactly.
So good words of wisdom, Anna. As we wrap up, is there anything you'd like to share with folks who are listening today about maybe how they should be thinking about what they're going to do, whether it's a career in science, you're an early career scientist, anything at all, whatever they decide to do, advice that you'd like to provide people?
Yeah, I think a really big thing for me is that I was very fortunate to have some incredible mentors along the journey, because scientific research can be very solitary. You're tasked with, creating new knowledge in an area that people may or may not have done research in before. And having mentors and champions along the way is really important. So a lot of my mentors come from the FDL community, but also outside of that, people that you can trust and rely on when you're feeling down, but also people that champion you and help you to your next career stage. So I've been very fortunate to have had amazing people that have been that for me. I'm trying to now pay that forward to the next generation of scientists coming up. So I think understanding both who can be that person for you and going out of your way and trying to find these mentors, but then also when you're in a position of power, using your, privilege and using your skill sets to help other people rise the ranks is really important. And the FDL community has, I think, demonstrated this really well over the last couple of years. The fact that we're invested in, the team's success rather than in any single person's success, and investing in each other's knowledge and growth has been really, really great. So I think that's something that I wouldn't be where I am now if it wasn't for great mentors and champions. So that's something that I just wanted to emphasize at the end.
Most excellent. Thank you. And thank you so much for spending time with us today. It's just always a pleasure when we get to hang out together, whether it's in person or like we're doing here today in the Wormhole. We're grateful for you and all that you've contributed over the years to the fantastic work that the researchers and faculty do at FDL. We look forward to the next time we catch up with you and see what you've been working on, perhaps at a future Wormhole.
Thanks, Jonathan.
Thanks. Thank you all for joining us. We'll look forward to seeing you again soon in the Wormhole.